hear me? Yes. I don't want to have to yell, but so what we're going to cover today, we're going to look at some definitions, kind of level set. We'll talk about what machine learning really is, as well as neural networks. Then we're going to look at some of the pitfalls that are inherent in those technologies and how those apply to cyber. Now, let me preface this with this. The outcome of this is not for you guys to be able to sit down and program your own AI application. As I started studying this, and one of the reasons I did this is because I had vendors constantly approaching me and telling me how they had this great new AI feature in their tool, or they had this machine learning thing, and I'd look at it and I'd be like, you know, I thought I understood what that means, and one of the two of us doesn't. So I thought I would take a look to kind of figure out what's really going on under the hood, which is the nature and the genesis of this. So it's really an overview, but you really have to define what those terms mean in order to have a conversation about how they work. So that's where we're going to start. So level setting with some definitions. And we'll start with intelligence. And that's the ability to both acquire and apply something that you've learned. Pretty straightforward. Great example, here you got a little kid, shortest, but he's doing the smartest thing that they can see. That is intelligence. This is not intelligence. So, any questions before we move on any further? Then you've got learning, and that's acquisition of those knowledge and skills by experience or study, right? And this is really where we kind of get into the machine learning part, because it's change influenced by your experience. And that's essentially how all of these technologies work in one form or the other. The difference is the how that we're into. So the artificial intelligence, what they're attempting to do is create a machine that can act the same as a human can do. There are two types of that. The first type of AI is what we call general AI. And when people talk about artificial intelligence or the Skynet thing, this is what they're thinking about. A computer intelligence that can operate on the same level as a human being. And if you guys remember Alan Turing in the 50s, the guy that was the Boston part, what he said was that his test was that you had kind of like a blind test. You have a person behind one door that the person interviewing them can't see, and the computer behind the other, that the person talking couldn't tell the difference between what was the computer and what was the human. And so that was the Turing test. So that would be something that has most of those characteristics. But then you have a narrow AI, and this is where the AI and machine learning kind of fits in, because it can do one part of what a human can do, and can do that really, really well. But the other stuff, not so much. Okay? So really, the best way to think of artificial intelligence machine learning is it's not brilliance, it's a savant. It can do one thing really, really well. Laser focused on that. Outside of that, good luck, because that's all it's designed to do. So that's where we get the machine learning. It's that narrow AI. Okay? So let's take a look at what machine learning really is. So it's really about using algorithms and statistical formulas to project output in a certain range. Now, one thing I don't want you to go away with is to think that it's just statistics. Okay? Statistical methods are part of it, but they're only a part of it. I have put something in me. So sorry. So there are two goals really. One is that these programs or these algorithms will pick up what's happening in their environment and be able to use that to improve themselves. Okay? Which basically means that the outputs of the program become new inputs. And that's what traditional programming, that's not the way it works. The way that our computers work today outside of AI and ML is that you have a program and data that go into a computer and you get output on the other side. But with machine learning, we're taking the data and the output and it's essentially producing a program that does something. So it's a little bit of a turn on how you have to think about it. And that actually becomes really important as you start looking at some of the methods behind that. The other thing with machine learning AI is that they want to standardize the machine learning so that you're not having to program everything from scratch, to be modular, like a lot of programming languages. So that's another one of the big goals, and we don't get a lot into that. I can show you some resources that will help you. Okay, so let's talk about the types of machine learning that exists out there. Any questions so far? Okay, I don't want to bore everybody to death, but I do want to cover this. So there are really three major types of machine learning. The first is supervised. And so I had, what was that? If you have your computer, what you do is someone takes two different groups of data. One that you say, this is the good set of data, and you're labeling all that, and then a bad set of data. And you feed that in one at a time, and you tell the computer, this is what we want you to find, this is the stuff we don't want. Okay? And through that, it's able to identify the things. You have to go back and say, okay, well, you gave me most of what I wanted, but this part of the data was bad. And that goes back as an input to the algorithm so that it learns and tries to process that out the next time. That's what supervised is. And there are two kinds. This is we'll get to the graph in a minute, but there's regression, which is using numeric values. We have classifications, which has either classes or tags. So the other thing is, if somebody here works in machine learning on your day-to-day job, you do it out of, so feel free to correct me if I've got anything wrong, but I've done quite a bit of research here. So that's supervised learning, pretty straightforward. And quite frankly, this is how human beings work, okay? You have a baby, and as that kid's growing up, to say, this is what we want you to do. This is how you walk. We show them how to walk. They start walking. They fall down. That's negative feedback. They are able to get to the cookie on top of the table, positive feedback. So that feedback goes back, reinforces that behavior. This is really how we work, is to supervise. Most institutional learning, like in your elementary school or college, that's how this works. You get something, this is what we want, this is not what we want, you test on that information, that's how this works. Then you have reinforced learning. And reinforced learning takes that data at the beginning and doesn't classify it. Puts it into the computer, and output is it tries to classify whether that's good or bad, and you go back and say, yep, that's what we want, this is not what we want. This is more like how we might study for a certification test, okay? You have to go out and find that knowledge, you read books, but ultimately it's you taking the test that tells you whether or not you figured that out, or applying that knowledge in the field. Okay? That makes sense? Then the third kind is unsupervised, okay? And with unsupervised learning, we take all of that data, puts it in, and the computer tries making sense of it. And then it reprocesses that data again and again, and continuing cleans that up until it gets something that it can't refine any further. And once it gets something that it can't reduce down, kind of like factoring in math, then that's its final output. Okay, that's what unsupervised machine learning is. And that really is what deep learning is. That's the difference. Deep learning is using iterations, and we'll take a look at what the model looks like in a second. But essentially, these are graphs of unsupervised and supervised learning, right? So this is where I'm saying I've got these two classes, one is good and one is bad. Unsupervised, the machine just tries looking at what it's got and saying, okay, this stuff kind of looks the same, and this stuff kind of looks the same. But the thing is, the machine can't give value judgments. It doesn't really know good or bad with that human intervention. It can just say, you know, one of these kids is doing something, right? This is not like this, is all it can tell you. Whereas with supervised learning, we can say, hey, this is bad or this is good, but humans have to evaluate and give that feedback. So that's a very important limitation. When you talk about the real automation of AI, it's still limited because computers don't have imagination. It can't figure out anything other than what you tell it. We good? Okay. So, what does deep learning do? Okay? So I love this. This is what society thinks it is. This is what your friends think it does. Mathematicians, other scientists think they're just getting rich off of it. But there's nothing to it. Okay? So when I first started thinking about this, I was like, man, I'm going to run a VM on this, and I'm going to do a demonstration for machine learning in real time. And it is boring as crap. There's nothing to it, okay? There's nothing more I could show you in a live demo, so I just took screenshots and stuff. But there's really not a lot to it. And there are multiple languages. It really depends on what you're trying to do. We'll talk about that after. So, really, so, methods. There are several major methods in machine learning, and we're just going to look at a few of them. One of them is linear regression, right? It's where one thing has a relationship to another, like in math, where you have y equals mx plus b, and that may be like, for example, hot dog bun cells and hot dog, right? They have some sort of relationship, positive or negative. Then another one is decision trees, okay? Pre-comments and stuff, and all you're doing is you have humans inputting what the rules are, and then the computer uses that to filter out. So, for example, if you want to eat a banana, you can look at the color, okay? If it's dark yellow, has black spots, I'm not really interested. But then, even if it doesn't have those, is it too soft or firm, I'm going to eat it. Decision trees are just complicated levels of that. Then you have Bayesian networks. So this is just a similar kind of graph that's explaining the probability factors that go into something. So this is an actual one that I ran some code on, but taking a misuse type to try to go to work. So from that, you have to look at several other factors, and those relate to other factors, and eventually all that leads to your final output. And then you have to give these probability factors for each leg of that tree. But essentially, humans is still saying what qualifies and what doesn't. Okay, it's really just a complicated probabilistic flow chart. The other is clustering. Okay, and we looked at this just a little bit while ago, but it's where you're taking these things and you're saying, okay, this group is distinct in some way from this group, or these two groups are distinct from this. All right, and here's a clustering graph. This is most commonly used in things like if you're having AI try to determine whether a photograph is a tree or a flat. Okay? And here's another one where this is actually U.S. Postal Service, where it's trying to read handwriting. And this is the scan from a clustering method. And you see which of those has a class number, so the class is number 3, and the novelty, how much it matches what it thinks a 3 should look like. And so you go up into tuning those. But that's what clustering is. Now, those are just a few of them. This is kind of a mind map of machine learning algorithms, and there's a lot to it. So again, this is not an extensive coverage of that. But the point really here, it's not rocket surgery, right? It's not, you don't have to go too far to kind of understand what we're doing. And all of the fluff marketing stuff is really still just probabilistic math. Now, neural networks are a little bit of a different animal, so let's take a look at those. All right. First of all, you have automated neural networks, and the most basic unit is what they call a perceptron. You have an input cell and output cell. And the reason they call them automated neural networks is because this is trying to mathematically model how the human brain works, the neurons. So let's say, for example, you're trying to figure out how to buy a house. So you say, well, I need a certain number of bedrooms, a certain number of square feet. It takes both those factors in and gives you a result, right? Pretty straightforward. But when you look at a neural network, and this is one example called a feedforward, you have input cells and output cells. So there are a lot of other factors that go into a house, right? Like not just the number of bedrooms and square feet, but the price or the style of the house. And then your ultimate result is what house you want to buy. But are those the only factors that go into buying a house? But they're not. For example, you've got these hidden cells. So I could also say, okay, I want to look at locations. So for each house, with a given location, it would calculate a value in the next location, and the next location, and the next location. But location is not the only other factor. You might have something out of the school district because you've got kids. So then all that gets recomputed at each level. And then that goes back to give you a value. And that's kind of the complexity of a neural network. It's taking all those small little calculations and giving you all of the permutations of that and trying to find out the best value. Now, this is why, another thing is these values, these hidden cell values can also be weighted. So if you have 3 kids at school age, that may be more important to you than the actual location. Or if you don't have kids, that might not be the important. But these hidden cells, okay, that's where the deep learning part of it comes, because that can be 50 levels of different computations. And you guys could probably think 10 of those factors off the top of your head for what would make a good house purchase for you. And all of those different levels is why they call it deep, because it's processing at every level for every permutation to come up with a value that ends up being your result. Okay? That makes sense so far? Okay. So, remember, this is only one of the very many types of automated neural networks. Some of them go back and put output back through an input and can really test itself back down. But there's a lot of them. But the important thing that we want to look at from a practitioner standpoint is, what does this all mean, right? What are the things that we have to watch out for when we're talking about machine learning or neural networks? So, one of them are training, right? So, let's say that you put your data in and it doesn't perform it performs poorly because you've underfitted. And underfitted means that you haven't really associated the different values that give the result that you want. Versus overfitting, where you've been really, really specific and sort of talk to the test, where you say, this is exactly what I want, and you type it down so much that only that exact pair of data is the match out of that algorithm. And both of those are problems. You really want that balance, right? You want it to be able to take the middle ground and figure it out itself without getting lost in the data or getting too focused on the one result that you gave it. And with the underfitting, you have a really high bias but low variance, and it's the opposite of overfitting. For the underfitting, you can give it more features. So you can say, well, I also need to have these two factors taken into consideration for my model. Or you can decrease how standardized you've done that data. Whereas with overfitting, it's kind of the opposite. Well, okay, I need to put less specific about my data, but I need to trim the data down a little bit. But here's the thing. Who's ever tried working with tested data in a live environment? It's freaking hard to do, right? And when you're talking about, I saw one modern paper, I've read 3 or 4 books for this and hundreds of papers, and one was supposed to be a state-of-the-art how neural networking applies for packet recognition and cybersecurity. And all of the data set they were using was from 1999. Okay? I mean, really, come on. How does that really apply to our modern computing environment? You can have that thing absolutely fine-tuned and be perfectly useless in the real world. Okay? And getting that data can be very, very difficult. And depending on which model, supervised, unsupervised, hybrid, that have a big balance. So at the end of the day, you can still get false positives even if you get your model balance because you haven't used the right data set. And when you buy a product from a vendor, do they show you what data set they use to achieve their output? No. They're going to show you what they want to do. When they run that demo, they're going to show you everything perfectly set up because it's probably the test data they use to create the model purposes, right? So be aware. The other thing is manipulation bias. So if we take a look at this statistical output, what kind of graph do you think we're going to get? So I'm going to go out on a limb and say whoever generated that data set had a predetermined outcome. Any takers on this? Okay. If somebody has an agenda behind that data, you've got a problem. And you don't necessarily know what that developer was doing when they created that rule set. Right? And how do you know that that's not a hidden agenda? How do you not know that's just what the vice president in charge of that division 6 months ago was really on about before he got fired? You don't. But you get this thing, and remember, a lot of those values, particularly in artificial intelligence, when neural networks and hidden cells, they're hidden. You can't see them. Okay? So you don't know. You just have to take their word that it does what you want to in your network. Clustering. So we talked about that, like separating out 2 different groups in the data set. So what's this? Math is math, right? Math gives you a certain outcome. Well, if we take a look at that same set of data, and we apply a parametric, which means you have a normalized data set, standard normalized curve, you have these two groups that the machine learning algorithm pulls out. Blue is one group that classifies, red is another group. Now, just from what you know from a very surface, does that look like it matches what the data set is in that population? Not really. But if I do a non-parametric circle classification, then I get a tight group around the inside circle, everything else is in the red group. That's a much bigger distribution. Okay? You're also very dependent on the assumptions whoever develops those software are making on what the data is supposed to be. Okay? If they assume that you're going to have a normal data set, for example, let's say you're doing throughput on your network. Sometimes it's going to be really low, sometimes it's going to be really high, but on average we'll have this level of data through the network, right? But what happens if it's end of year and all of a sudden everybody's putting stuff through? Now that algorithm, which is expecting a normalized curve, is something else. And that machine is going to make assumptions on what that data means. And that may not be what you want it to output. So what you normally hear when people want to bring in machine learning, particularly like user behavior analytics, they'll talk about baking time. Okay? And I was recently in charge of a pretty large network with about 6,000 end users spread out over 10 different buildings, several different states. And this vendor came in and said, hey, we can have our proof of concept work in your environment in 3 weeks. I said 3 weeks. I've been here for 12 months, and I don't know what's going on for enough. You're telling me your device is going to figure that out in 3 weeks? That would be a neat trick. Well, 3 weeks is kind of a place to get started. And the reality is, it's going to take a year to find out what normal is.
Month end, year end.
Month end, year end, and you're assuming that normal doesn't have a bad guy in the middle of your system. Because if that's what your AI baselines, that becomes your normal. Okay? Which is exactly what happened when Microsoft sold a gift to us last year. You know, we all thought that having that SMB at the very beginning, we've been doing that for 15 years. That's just normal. Every device we've had for 15 years has been passing that traffic through with, hey, that's what Microsoft's supposed to be doing. And we find out that every national government's been taking our data out in a dump truck and waving at us as they drive by. And we've been opening the door for them as they go. Right? So you can normalize bad traffic just as easily as you can normalize good traffic. So, things to consider. Questions? Okay. Now, let's go back to that neural network assumption. Okay. So we've got locations in school districts. And remember, those things are weighted values. What if you don't really care? What if you're an empty nester, you've got all your kids who graduate from college, and what you really want is to live at the beach? Would that first set of data that we looked at give you the result that you want? Yeah. It's going to tell you what's really good for a 32-year-old couple with kids that are all under 15. But that might not be what you want. And those things are weighted. It's not just what you're looking at, but the values each of those hidden values can have and how that influences your eventual outcome. And remember, in neural networks, the machine itself can go back and say, well, that doesn't really match the data that we're seeing, and it can change those values as you go. So this means a couple of things. You've got an assumption by a human, which has been attempted to be modified by a computer, assuming what the data is supposed to be. You start making decisions, but in a real artificial intelligence scenario where you have the machine making decisions on the algorithm itself, it's also changing. So the assumptions you made yesterday, you put that same data through tomorrow, the exact same data set, and you can get a different result because the computer is tweaking. So essentially, you've got decision management being made without change management because the computer is smart. Well, you know how that works out for you.
Is it really?
So, questions? Okay. The other thing is, you guys familiar with the term PFM technology?
You know, an email address.
Pure freaking magic. It's black box. You don't know what those are. You don't know when you get your algorithm how many levels deep that A&N might be. Okay? They could be making 40 assumptions, of which you would only find the 2 of them. But you don't know. All you know is that data goes into this side of it and magically outputs results. And because the computer did it, it must be right. Kind of like working in a company your whole life. You tell somebody the same thing every day for 5 years. Nobody believes you. They hire a consultant. It happens in 3 days. Whatever, right? Because the consultant said it, it's better than what you did. Now because the machine is doing it, but we have zero visibility into that without getting into the source code. And that was what I was going to demonstrate by showing code, but honestly, it's about like watching graph. Also, so this is C++ code, where somebody has done the classic hello world, right? Artificial intelligence systems determined that was 80% likelihood of being malware. Hello world is malware. Okay? Because there are assumptions going into that. And sometimes those are very poor assumptions. Any human who's ever coded can look at that, 5, 6 lines of code and go, yeah, I get that. But the computer is like, there's a bad guy. Now, multiply that times every packet coming into your network, every app that one of your users is running. You have a very significant problem at that level. Image perturbation. So this is really great. There are actually ways that you can very easily fool AI as well. So this is an image where a computer is going to analyze it and said, there's a 57.7% chance that that is a panda. You overlay that with this pattern, you're going to tell you it's 99% chances to get it. They have some really funny ones, and I can show you pages of this, where it thinks that mops are sheepdogs, or fried chicken is labradoodle, or a chocolate chip muffin is a chihuahua, because they can't tell the difference. Right? But we're using this stuff all the time. And there's some real security implications. And I'll give you a really good one. I don't allow my children to have any social media account until a certain age. But for the last 5 years, my youngest daughter, every time her image gets processed when somebody else posts an image out with their friends, it's got her in it, it identifies her as my wife. Okay? Because their image recognition algorithm sees enough similarities, it's identifying her, even though I really don't want my youngest daughter identified today. But it's putting that everywhere. And I see tags all the time about my wife, they're my youngest daughter. Okay. Extend that out times the population of the world. I don't see any way that can be resolved. And so, the intelligence thing, that's an intelligence with limits. There's also, some of those, holograms, the images you look at and close your eyes.
Magic eye.
Yeah, that kind of stuff. So it's, where it sees a pattern that's an optical illusion for you, but it thinks it's an AK-47 or a baseball bat, and you look at, like, I could stand on one leg with 2 eyes closed and still not get there. I don't really get it. That same pattern, by the way, has been shown to also fool things like the cameras that identify numbers or license plates. If that image, and remember, we're all professionals, you're not allowed to use this, but if that kind of image is on a sticker on your license plate, that is enough to fool the computers running AI identification on your license plate without being able to read letters. So humans have to go look at that. And so that has some pretty big physical security implications as well, right? All somebody has to do is put that kind of sticker on their hard hat, and all of a sudden you don't know who it's to. There's also some funny ones where people wear just like a funny pair of novelty glasses, and then it thinks they're like pretzel launchers. And then this was last week, right? In a relatively untimely bit of humor, I said, I put a post on LinkedIn and Twitter that said, Skynet claims its first victim. But the reality is that there are some very real dangers that releasing AI into the environment today. Because that AI is still making assumptions programmed by people you don't know that are impacting every facet of your life today. Okay? And some of these it's not just when they're wrong. Some of it's when it's accurate. So, you know when you go to the grocery store, you have your little loyalty card, right? You scan it in, it gives you 5% off. Of course, as information security professionals, we know they're exploiting the crap out of that, and they're tracking everything that you do, right? So some of you probably heard this. This was about 3 years ago. There's a guy who goes to Target with his daughter, his 15-year-old daughter, and they scan out, and the coupons print out on the back of her receipt are all for infant diapers. And he goes absolutely ballistic. He actually ends up calling the corporate headquarters for Target because they're assuming that his 15-year-old daughter is having promiscuous sex, and she is a fine young lady, and what are you doing? Well, it turns out she had been and was, but it knew from her buying habits of non-baby related products that gave a very, very high probability that she was going to her first trimester of pregnancy. She knew that. The computer knew that. Dad didn't. Okay? It made national news. Okay? That would be disturbing as a father or as a child. Right? So, where do these apply for cyber applications? We can talk about this in a lot of detail. I tried hitting the highlights. There are actually a number of really good papers, and there are even more really crappy papers. Because, frankly, a lot of people have no imagination, but they really, really like to write papers. I don't know if you get like check boxes on the academic. So be careful. I do have an appendices that will give you some of the better ones I've got in this. But let's look at some of the white assets, right? So first of all, network management. There are actually some very empirical studies where knowledge-based networks are driving real change at the AI level to help you manage your network in real time in a way that humans don't have the time or the patience or the scope to do, because you just can't look at everything. With AI, it's all kind of numbers, right? Then you've got data visualization and KPI tracking. That's really obvious. We're not like the mainframe. We're more like the PC, right? But AI can take these huge buckets of data, find patterns in that, and alert you about what you want to know about, or to let you know leading or lagging indicators, where it's about your financials, about your security program. And there's the patterns and complex logs. And there are a lot of papers where people have looked at those. But again, remember, some of those are using really poor data sets, and so you get kind of questionable outputs. And here's the thing. When I read through all this, one of my big takeaways, you remember when they were talking about the real growth of printers in the workplace, and they were saying that, well, actually, even before that, computers are going to replace human beings. Human beings want to be working 15 hours a week, and computers will take all this work that you're doing. I don't know if they've looked at my time card lately. I'm not getting very many 15-hour weeks. How about you guys? Then it was printers, right? Printers are going to eliminate the paper companies. Or I'm sorry, as they did away with printers and everything goes digital, we don't need to print as much stuff out in paper, right? Anybody been in an office that I've sure been lately? Right? And you got the clean office, the clean desk policy, because you walk by somebody's desk and they got the Leaning Tower of Pisa. Well, that's not happening. Likewise, AI is not going to replace a person, because AI can't do critical thinking. It is incapable of doing critical thinking at this point in history. And I thought about there's a really neat graph that shows kind of where we are, or at least kind of the height layer. But ultimately, it's not going to replace people. But here's something that's really interesting. We talk about the Internet of Things with artificial intelligence and machine learning. What those essentially are, if AI and ML is the brain, IoT is the senses. Touch, smell, vision, right? So you're going to be able to extend that in all facets of your environment in your workplace, or your home, or the world. But so are national governments and terrorists, right? So kind of everything we use for good and use for evil. Just remember, this isn't a silver bullet. And this one white paper listed to artificial intelligence had a really great quote. But it basically said that the main point here is that, yeah, it does stuff really fast and really well, which ultimately means that AI can fail in ways that humans can't even scale today. Okay? It can process data faster than you can. It can also make mistakes a whole lot faster than you can too. And once it starts making one, sometimes it's liable to make a circular loop where it amplifies the effect of that. Now, for the bad guys, what we're talking about, data poisoning. Okay? If you can go to mess with the source data, you then change what that computer thinks is happening to the environment. But this is more extensive than ability to edit and change logs. Okay? It extends much further than that. Every IoT device, all that kind of thing. Also, it scales the attack, which includes not just the digital world, but for changing photographs. Okay, like we looked at earlier, what can invalidate the AI on a security camera or voice over IP, and those are realities. Also, it's able to exploit vulnerabilities a lot faster than a human can because it can do it every time. It doesn't have to sleep. It doesn't get tired. It can also discover new holes really fast because it's good at seeing outliers. And here's one thing. So I was in the Army for a long time, and one of the things we talked about a lot was on Abrams tanks, my last job. And when you put a bad guy tank in the site, you're not thinking there are 4 human beings in there. I see this metal thing with a gun that's about to shoot at me, and I want it to go away. And there was always this fear that people would lose, through abstraction, the fact that you're really killing 4 people by pulling that trigger. Okay? With AI, you're just setting something out there to run. And you're not really thinking through all the implications or how widespread that could be. And so that can amplify what the bad guys are doing. The other thing is uniqueness of data. Remember, this is ultimately about finding patterns. And if they're outlier data, it doesn't really know what to do with it. Because remember, it can't make value decisions about the data. Only humans can really do that. Another really good quote from that same thing. Artificial intelligence is dual use in the same sense that human intelligence is. Okay? And that's a good takeaway, is that it can be used for both good and bad at the same rate. So, what we took a look at is we took a look at definitions, we looked at machine learning, the type and the methods used. We took a look through neural networks, we looked at some of the pitfalls, errors, assumptions, and biases, as well as how it can be used in cyber applications. Here are some of the resources, references that I used. So I have literally, guys, we'll post this stuff up. You don't have to take notes or whatever. I'll get this out as soon as we can. But this one right here, I really want to point this one out. John Zwala, he is a guy in Philadelphia who, at another BSides conference, as I started looking around, and I only found this last week, but his presentation was very, very similar to mine, so he was helpful in giving some additional data. And I have links here to both his presentation as well as the slide deck itself. So, with that being said, does anybody have any questions? Yes, sir.
What platform do you use today to implement machine learning models today?
I looked at Torch and Ubuntu, but there is actually... So there was a book, let's see if I got it here, that I listened to it on my phone, that I really liked. It had a great overview of machine learning, and I should have had that up already.
It's not the massacre algorithm.
The name of the book is Machine Learning for Beginners by Ken Richards, and it had a really great breakdown of most of the major machine learning systems, what they're really good for, who's using them, which ones are open source, which ones work better with CPU or GPU. So that's a great book if that's where you want to go. Or shoot me something on LinkedIn, and I'll send you my notes I took when I read the book. Thank you.
Package Publishing, I think it's PAKT or PACKT. Something like that.
PCFAT, yeah.
They have a whole bunch of stuff in their Python. They have all kinds of data science, machine learning.
So one thing I'm going to assure you is you're not going to have a problem finding information. You know, there are websites with hundreds and hundreds and hundreds of linked articles. Finding useful information, wiping security logs is a different thing. So I'm not telling you these are the best resources, but to me these are the most clear to get you to the point faster. You have a question, sir?
Yeah, so we've heard a lot of recently, at least in the media, about algorithms that, well, you give it to the machine figures it out. But I guess this is some type of form of machine learning, but I'm not quite sure where it fits. But we don't know how the machine came to the conclusions. This is sort of this black box we accepted as rote that, oh, it's magic. Now, as a programmer, I did expert systems a long time ago in the 80s. That doesn't make any sense because I gave it a bunch of rules. If I had good diagnostics, I could write down, I could have a debug log that said I went through the tree like this. The algorithm did it, the computer executed it. Why can't we do it? But there's apparently a class of machine learning that we don't know how the machine figured that out.
So the worst one for that are recursive neural networks, RNNs. And that's because it takes output, puts it back in as an input, and the machine takes a look at it and goes, oh, well, I need to adjust this and this to trim down that data. And those are those hidden cells, those hidden neural nets. So you don't know what it's changed. And when you have something that, I mean, think about it. How many times have you had in your practical environment where somebody did a change that affected production, but nobody really knows why? I was at Blue Cross Blue Shield one time, and somebody was working on the database from home and shut down a new system for 3 days. Okay? And it took forever to figure out what happened, who did it, and then it took about a day and a half to unscrew all the things that he had done by literally putting a comment into a sequence there. Okay? Now you've got a machine with 50, 100 levels of changes it can make, all of which are, right? You can't see it. It's a black box.
Okay.
It's PFM.
So it's a needle in a haystack. There's too much.
But it's a change affecting an assumption versus a mathematical algorithm that's also making assumptions on the shape of the data. And so that cone of what that's changed ends up exponentially growing.
Bayesian classifiers suffer from this very much. There's people who write Bayesian classifiers will tell you they can tell you whether the difference between something that's between 80 and 90 or something that's between 50 and 60. But they can't tell you the difference between 52 and 53. And they can't tell you the difference between 58 and 62. Because a lot of the ways that classification occurs, especially in Bayesian models, is pretty much PFM.
And I think part of it is they could write a debug log out for you that doesn't even know where you're at.
I mean,
You just could not.
Because of the exponential.
Yeah.
right, even the mathematicians don't know because you've had a billion logs go through to train this. Call it half a billion. Call it half a billion good and half a billion bad.
Okay.
And from that, it has defined characteristics that are good and bad, and it's drawn its line.
Do we have time for one more question?
Yeah, just really quick. I was wondering if you guys have heard about Apache Metron. It's an open source project.
Yeah.
It leverages Hadoop for big data, things like Apache Storm for streaming analytics, and it aims to address two things. So one is, you need a lot of data to train these models. You need to collect DNS data, you collect firewall logs, your intrusion detection systems, internal activity, right? So big data gives you the cost-efficient way to do that. But you can also publish your machine learning algorithms, which you can train either in Python or your tool of choice, and deploy them on Metron. So the nice thing is it just gives you that already architected platform, and it's an interesting one that I'm learning right now. So just figure it out.
This is part of the notes in that book.
Metron. Yeah. Yeah, Spark is another, yeah.
All right. Well, guys, thank you very much for your time. I don't keep everybody. If anybody has any separate questions, feel free to ask me afterwards. Otherwise, you've got my contact information. And thanks a lot for your time today.